This video pertains to Chapter 2 of the Energy Unit, which discusses the carbon footprint and how to calculate carbon footprint. So if you look at the top of this, you can see that the carbon footprint is equal to the moles of carbon dioxide over the amount of energy that would be released in a combustion reaction. If I take this reaction that I have below here, it's ethane plus oxygen forming CO2 and water, and it says that it releases 2,500 kilojoules of energy to it. So you balance the equation, you see we have two C's here, so 2 on front here, 6 H's here, and there's a 2 there, so I need a 3 on front here. I got 4 oxygens here, 3 oxygens there, so it's a total of 7. Write that over 7 halves to sense the fact that it is a diatomic. So what this tells us is that 1 mole of C2H6 will release 2,500 kilojoules of energy. So now, when calculating carbon footprint, what you need to do is you're going to take the number of moles of carbon dioxide, which is 2, and you are going to divide that by the amount of energy released in the reaction, so 2,500 kilojoules. Typing that in your calculator, you're going to see that the answer is 8 times 10 to the negative 4th, and that will be moles per kilojoule. So how you evaluate this number right here is it's all based on your carbon footprint. The larger this number is, the greater the carbon footprint is. The smaller the number is, the smaller the carbon footprint is. You're looking to have the smallest carbon footprint that you can for the environment. So this, just to conclude, shows you what you need to do, and if you had any type of comparison between one versus the other, how carbon footprint does apply based on combustion reactions. The purpose of this video is to just give an example of showing you efficiency of energy transfer and a calculation of this. So you can see at the top the efficiency of energy transfer is going to be the useful output over the total output times 100%. So an example of this, let's just say that we have a power plant which releases 6,000 megajoules of energy when burning coal, and let's just say that it's 15% efficient with this. So using this formula, this is going to represent my useful output, but we don't know what the total output is going to be, so we have to solve for that. So you're going to say 6,000 megajoules divided by X, which is going to be the total output, and that's going to be equal to the ratio of 15 over 100, which is just 15%. When you cross multiply, you're going to get 6,000 times 100 equals 15x, divide both sides by 15, and then you're going to see that X equals 40,000 megajoules. Now, let's just say 40,000 megajoules is the amount of coal or amount of energy that you actually have to do produce if it's 15% efficient. And for example's sake, let's say that 30 megajoules of energy is released for every 1 kilogram of coal that is burned. So we're trying to figure out, well, how many kilograms of coal that will we actually need? Well, since this right here technically is a ratio, you could write this 30 over 1 or 1 over 30. And if you're using that based on this number right here, you're trying to get those units to cancel out. So if you say 40,000 megajoules, and using these ratios, we're going to want 1 kilogram over 30 megajoules, so the megajoules cancel, which tells us that it's 1 kilogram over 30 megajoules. The megajoules cancel out, and that leaves us kilograms as my final answer. So 40,000 divided by 30, and you're going to get an answer of 1,333 kilograms of coal. And I hope that helps explain how to do your energy efficiency and calculations involving the energy efficiency and converting it into grams.